Hi, this video will be going over Sn2 reactions, covering the conditions to make the reaction happen, the mechanism by which it happens, and the energy diagram of while it's happening in the reaction kinetics. To start off with, we'll go over why it's called Sn2. We call it Sn2 because it is a substitution reaction. So we have something like an alkyl group bonded to, let's say, a halide, and we end up substituting this halide with a different one. So that's all it is. We end up with an R X prime with the new halide. That's just the general substitution reaction, and then we call it Sn2 because it is a bimolecular reaction, meaning that it depends on both the concentration of the reactants and the products to make it go forward. Low concentration of reactants or products will decrease the rate of the reaction. So let's start looking at the mechanism by which it happens. We start off with some carbon-containing compound. This one right here, it has a stereocenter at this central carbon. And you can see that the configuration right here, you could check the configuration for yourself. But what happens is we take a nucleophile. The nucleophile is any atom that wants to be bonded to a nucleus, lover of nucleus. That is because it has lots of electrons to give away. So usually nucleophiles have a negative charge because they have an excess amount of electrons. What happens is our nucleophile will see an electrophile like this carbon. This carbon is losing its electrons to this bromine. So there's a partial positive charge going to the bromine. It's losing electrons to this oxygen right here. So there's another dipole moment going there. So this carbon is very electrophilic, meaning it wants electrons. What happens is that the electrons in our nucleophile, whatever it may be, will go and we call it attacking the carbon molecule. So they'll try to bond to the carbon. And what happens there is there's actually a transition state in which the carbon is partially bonded to our nucleophile, as well as we'll call it a partial bond, as well as bonded to the other things that it was connected to. So we have our alkyl group, our OH, our isopropyl group, and then it is also partially bonded to what we call the leaving group, which would be this bromine. Now, our bromine is a good leaving group because it likes to have a lot of electrons. When it leaves, it'll take the electrons that are in this bond with it. And a lot of times we see bromine in its anionic state. That's because it likes to be in that type of state. And what happens in this transition state, we'll denote it by these brackets here, is that the electrons forming in this bond are bonding more strongly to the carbon, which causes the electrons in this bond to go away to the bromine, so that carbon retains its octet of having only 1, 2, 3, 4, 5, 6, 7, 8 electrons. And in doing so, we get what's called an inversion of configuration. And we can kind of imagine that the stereochemistry just flips. So if this was an R, I'm not completely sure, I haven't checked it yet, our resulting molecule would be an S. So I'll show you what the entire reaction looks like a little more cleanly. We have our carbon with our bromine, and we have a little isopropyl group, our alkyl group, and our alcohol. We have our nucleophile. Let's say our nucleophile is anionic iodine. It goes and attacks the carbon. We draw our arrows from the electrons to the new bond that'll be being formed, and subsequently our bromine takes some electrons with it, forming a new bond between the iodine and the carbon. But now in this case, our OH group would be in the back because there was a inversion of stereochemistry. Our CH3 is here, and here's our isopropyl. And so if this was an R, this would now be an S molecule forward. Now let's talk about our energy diagram. What's happening here? Well, this state right here, we have our nucleophile plus our group, the leaving group. And once our nucleophile bonds to create that transition state where the leaving group is still attached, we get a very high energy transition state. So that's what we would put for right here, is this transition state. We'll denote it by this sign. For when it's high energy, the R group has almost 10 electrons bonded to it. And then finally at the bottom, we see that this is an exothermic reaction because the resulting bond lies lower than the starting molecule did on the energy diagram. And that is when our nucleophile is now bonded to our R group. Let's talk about some of the conditions that make a good Sn2 reaction. So first of all, we need to have a good nucleophile. We'll say that any group on the periodic table, so I'll just draw out our periodic table, and we have a bunch of stuff going across, bunch of elements going down. Any group more on the right side of the table will be less nucleophilic, so we'll say nucleophilicity decreases from left to right. And any group at the top of the periodic table will be less nucleophilic, so from top to bottom, nucleophilicity decreases as we're going from bottom up to the top. So fluorine at the very top right here would be a very bad nucleophile. But as we get to things like carbon or nitrogen, those would be a little better nucleophiles. And again, halides like iodine or bromine would be a lot better nucleophiles than fluorine. Just to sum it up, we want something that is polar and aprotic for our solvent. Unlike something like water, where it is polar but has protons to donate, we want something maybe like a nitro. This is polar but has no protons to donate. There's an inversion of stereochemistry. We want our nucleophile to be a strong but non-bulky nucleophile, so something like iodine would be great. Something like T-butoxide would not be a good nucleophile because it's so bulky. And then we want our substrate to be more unsubstituted, so a methyl or primary substrate would be a lot better than a tertiary substrate, just because our nucleophile wouldn't be able to get in there and make the attack on the electrophile. That is our summary.